This is problem 5.37 from the Mechanical Vibration textbook, RAW 6th edition, and we will find the natural frequencies of the disc mass spring system shown in the figure. The first step is to find the equations of motion. I will draw the free body diagram of the disc, and I will assume that it's rotating clockwise. The pin creates two reactions, and since it's rotating clockwise, the spring creates a force that is K1 times the displacement of one end of the spring, which is theta r. Now, to find out the force of the other spring, I will first draw the free body diagram of the block. And I will assume that the block is going down, and I will assume that x is greater than theta r. That's only to give a direction to the force, which the spring force is the constant of the spring times the relative displacement between the two ends. Considering that x is greater than tr, then the force in the block goes up, and by action and reaction in the disc goes down. Let me do now the equations of motion. I will take moment at point O, and external moment will be equals to kinetic moment. The moment done by the force of the spring is R times K1 theta R and negative R K2 x minus theta R. And that's equals to the mass moment of inertia times theta 2 dots, which is the acceleration. And that's negative because this is rotating clockwise. The mass moment of inertia of a disc is 1/2 mass r squared. And then I have that the first equation of motion is 1/2 m r squared theta 2 dots plus k1 r squared plus k2 r squared times theta minus k2 r x equals to 0. Now, for the other equation, I will add forces in my vertical direction. And I have K2 times x minus theta r equals to negative mass times theta 2 dots, which is acceleration. And I place everything in the other side of the equation, and I get my second equation of motion. I have two equations of motion for 2 degrees of freedom system. And please notice that the first equation that I got from the disc also has x as a variable, and the equations for the block has theta as a variable. That means that those equations are coupled. Now, let's write the equation of motion in terms of matrix form. Mass matrix, which is then 1/2 im r squared, that's theta 2 dots, and then I have 0 multiplied x2 dots. Then the stiffness matrix, the first term will be k1 r squared plus k2 r squared, that multiplies theta, and I have negative k2 r that multiplies x. And that will be equals to 0. My second row will be 0 and m that multiplies x2 dots, and then I have negative k2r and k2 that multiplies x. This matrix has the form mass matrix, acceleration vector plus stiffness matrix times the displacement vector equals to 0 vector. Now, the solution of this type of system is a harmonic function, which can be written as an amplitude times e to the I omega t. And if we derive twice this expression, we get that this is x2 dots, which is the same amplitude, and since I derive it twice, is I squared, which is negative, and it becomes negative omega squared e to the I omega t. We insert this solution into our equation of motion in matrix form, and we get the following. And this matrix is multiplied by the amplitude e to the I omega t, and to find the omega we make what is in the bracket equals to 0. And since this is a matrix, we have to calculate the determinant of that matrix. So therefore we solve the eigenvalue problem. And for that, we solve the determinant of k minus lambda m, k being the matrix, stiffness matrix, and m being the mass matrix. For our problem, we have that this will become the determinant of k minus lambda m, and that determinant is equals to the k1 r squared plus k2r squared minus 1 lambda 1/2 m of the disk r squared, and this is the second term will be minus k2r, and the third term k2r, and the last one is k2 minus lambda m, and that's equals to 0. And then let me multiply all those terms to get the determinant. And the first term, I will make the mass of the disk equals to m sub 0 to make a difference of the mass of the disk and the mass of the block. That multiplies k2 minus lambda m, and then I have minus k2r squared. Let me expand this expression by using the distributive property of the multiplication. And then using a little bit more algebra, I can get a quadratic equation. So let me do that and write a final polynomial, which is 1/2 mass of the block times mass of the disk lambda squared minus k1 plus k2, all that multiplies the mass of the block plus 1/2 mass of the disk k2, and all that times lambda plus k1 k2 equals to 0. And this is the characteristic polynomial that when we solve for lambda, we will get the natural frequencies of the system. In order to continue, let's just assume some values for this problem so that we can actually solve it numerically. I will assume that the mass of the disk is equals to 20 kilograms, and it has a radius of 0.5 meters. I will assume that the block has a mass of 10 kilograms. And then I will assume that both springs are equal, and I have a spring constant equals to 1,000 newtons over meters. So my equation of motion in a matrix form looks something like this. One half of m r0 is equals to 5, and the mass of the block is 10. This theta 2 dot x 2 dots, and this stiffness matrix is equals to 500, negative 500, negative 500, and 1000. And that multiplies the displacement vector, and that's all equals to 0. Now we get the determinant, and then we get the same characteristic polynomial but with our values. So that will be 500 minus lambda times 5, negative 500, negative 500, and 1000 minus times lambda. Let's get this determinant. And the characteristic polynomial for those values is equals to 50 lambda squared minus 10,000 lambda plus 25 times 10 to the 4th. And that gives me a value of lambda 1 equals to 29.29 and a lambda 2 equals to 170.71. So that becomes that omega n1 is equals to 5.41 radians over second, and omega 2 is equals to 13.07 radians over second. I always order the natural frequency to lowest value to higher value. With those values of lambda, I am able also to get the vibration modes for each of these natural frequencies. For that, I will solve the eigenvector problem. To do so, I will input that lambda 1 that I got and the lambda 2 in my matrix K minus lambda m times my vibration mode or vector. So let's do that for lambda 1 equals to 29.29 in my matrix that was 500 minus 5 lambda and minus 500 minus 500 and then 1000 minus 10 29.29 times 29.29, and this matrix multiplies my vector. This vector, remember that this leads to two equations, but those two equations are linear dependent, so it represents the same information. So what we do is use only one of these two equations and assume a value for x1 and then get x2, because what we care about is a proportion between x1 and x2. So let me set up x1 equals to 1 and I solve for x2 and I get a positive value of 0.707. And these two values represent the first vibration mode. Which is 0.707. If we do exactly the same for the second value for lambda, lambda 2 is equals to 170.71, and we input that in our matrix, that is 500 minus 5 times 170.71 minus 500 minus 500, 1000 minus 10 times my lambda, 170.71. Again, that leads me to two equations, but they represent the same equation. They are linear dependent, so we have only one equation. I will use the first one, and and that will allow me to calculate the second vibration mode. Again, I will put the value for x1 equals to 1, and I get that the value for x2 is negative 0.707. Therefore, my second vibration mode is the vector (1 minus 0.07). And if we want to physically see what those represent, it means that when I rotate my disk unity, then the block moves 0.707 in the same direction. And the second one means that if I move rotated this one unity, the block moves in the opposite direction, 0.07. And that represents the solution of this problem.